All right, this video is CC12 equilibrium. I think you would have done this towards the end of year 10. It's a super short topic. There's not much that you need to know, so we're just going to run through these questions together. First of all, you've got this arrow. Now, usually when we're writing a chemical equation, we write the arrow like this, but in this case, you've got an arrow that looks like that, and you want to know what the arrow means. And it means the reaction is reversible. By that I mean, usually you turn the reactants into the products. Once you form the products, you cannot go back. If you see this arrow, you're going from the reactants to the products, and when you make the products, they can be reversed into the reactants. Okay, so reversible reaction means as soon as you form the products, they can be reversed into the reactants. Some reactions do this, most don't. So if you think of a typical example of a reaction, you're baking a cake, that is a chemical reaction. Your cake doesn't turn back into eggs and flour and sugar. So it's not all reactions that can do this, but some reactions can. You turn the reactants into the products, and then the products go backwards to the reactants. One of the most common examples of a reaction that does this is between nitrogen and hydrogen to form ammonia. I'm just asking you to write a word equation, so I've given you all the details you need. It's nitrogen plus hydrogen. Now this is a reversible reaction, so I'm going to use that arrow, and the product you're forming is ammonia. And you do need to know this reaction off by heart. You need to know that you're forming ammonia. You also need to know where we get the nitrogen from. Okay, now we learned when we studied the atmosphere that 78% of the atmosphere is nitrogen gas. So that's where we get the nitrogen gas from. We just extract it from air. Now remember, the air is not pure nitrogen, you've got oxygen in there as well, you've got carbon dioxide. So what you would need to do is you would need to cool and condense the air. You cool and condense the air, so you turn the air around us into a liquid, and once you have the air as liquid, then you can separate the nitrogen from the oxygen and carbon dioxide using fractional distillation. So we get nitrogen from the air, but to separate it from oxygen, carbon dioxide and argon, that's the other one, we have to cool the air down, turn it into a liquid, and then use fractional distillation. The other thing we need to make ammonia is hydrogen. So where do we get the hydrogen from? Hydrogen we typically get from crude oil, again, which we studied recently in fuel. You typically get it from crude oil. Your other option is to take water and use electrolysis. So remember, electrolysis, you're using electricity to split something up. If you split water up, H2O, you're going to get hydrogen and you're going to get oxygen. So you can split up water using electrolysis and you'll get some hydrogen. That is very expensive, so usually we get hydrogen from crude oil. Remember, crude oil is a mixture of hydrocarbons that all contain hydrogen, so you've got lots and lots of hydrogen. So you get your nitrogen from the air, you get your hydrogen from the crude oil, you react them together and you make ammonia. And they do this in industry on a really large scale, and the reaction is called the Haber process, after the guy who came up with the reaction. And he realized that the best way of making ammonia was using a temperature of 450 degrees Celsius, a pressure of 200 atmospheres, and an iron catalyst. So this was the best way to make ammonia. You need to know these temperatures and pressures, including their units, and you need to know that you use an iron catalyst. So you're using a high temperature and a high pressure and a catalyst. All of these things speed up the rate of the reaction because you get an increase in the frequency of collisions. And it was the guy named Haber who realized that these are the best conditions. Now we're trying to make loads of ammonia because ammonia is useful. You use it in fertilizers to help crops grow. You use it in dyes if you ever dye your hair. You use it in explosives. So because this is a really useful product, we make loads of it. And the guy who figured out the best way to make it, he actually got a Nobel Prize for this, but these are the conditions he chose. Now the last little bit is called equilibrium, and you'll be asked to explain what is meant by equilibrium. Now we said that the reaction was reversible. So I'm going to write out the symbol equation here for this reaction. All right, so this is the Haber process. Nitrogen and hydrogen forms ammonia, and we said that it was reversible, and that means that the forward reaction occurs forward reaction is going from the reactants to the products, just like we always do. But you've also got what's called a reverse reaction, where as soon as the products are made, they reverse to form the reactants again. And if something is at equilibrium, you need to know that the forward and the reverse reaction happen at the same time. So it's not a case of the forward reaction takes place, you make all of the product, and once you've got all the product, then the reverse reaction happens. And then once you've got all the reactants, then the forward. That's not what happens, all right? So you get some of the forward at the start, you make a bit of the product, then the reverse reaction kicks in while the forward is still going on. So these two processes are happening at the same time. And they're happening at the same speed. So we say it's at the same rate. Same time and same rate. And effectively what happens, if you've ever been on like a treadmill, all right, and if you're running at the same speed as the treadmill, you're working and the treadmill is working, okay, so you're both still moving, but because you're going at exactly the same speeds, you don't go anywhere. And that's what happens with the reaction. If the forward or reverse happen at the same time, at the same speed, they effectively cancel each other out and you stop making more product. And this situation is called equilibrium. All right, so what you need to know, that arrow means reversible. If you have a reversible reaction, you can have equilibrium where forward and reverse, same time, same speed. Other thing you really need to know is just this actual reaction. It's called the Haber process. Nitrogen and hydrogen, where do you get them from? What conditions do you use?